Thank you for this very kind introduction. I'm very happy to be here at both the KTH and Digital Futures Center, and I'm very grateful for their generous support. Also for the IT Society Distinguished Lecturer. My actually VLs ends at the end of this year, so I thought I'd take this opportunity to give this talk. So. This is joint work by my collaborators that you can see from Macquarie University, also in Australia, and also this project is funded by Australian Research Council. So let's get started. So hopefully you can hear me on Zoom, okay? I hope. The context of this talk is differential privacy, and this is a widely used privacy-enhancing framework. And notable examples of the use of differential privacy is actually in recent years, it has become more and more, which is US Census. Probably the most notable example is that since 2020, they are using in their census release data. And even companies like Apple, Microsoft, and Google do use variations of differential privacy. So why we are here is that despite the widespread use of differential privacy, some of its properties, especially when it comes to Bayesian inference attacks, is not very well known. So what we are going to do in this talk is that we are going to understand some of the aspects of differential privacy through using tools from information theory and quantitative information flow, which is a subset of information theory. And this work is actually accepted in CSF next year, and a preprint of it is available on arXiv as well. And I'm happy to talk to you offline if you are more interested in the technical details. I have some technical details in the talk, but try to also limit it. For people who listen to my talk on Wednesday, there are 2 slides that are kind of common, so please bear with me about that. What the motivation for differential privacy was that existing mechanism, so-called mechanism to anonymize data and make data private didn't work. So for example, there is a very famous example that if you just remove personal identifiers such as name and telephone number and exact address, or some very personal information from a data set and release it, that is definitely not enough, because people can cross-correlate what you have so-called anonymized with other things that are publicly available and cross-reference that. And actually, one of the first examples of this, an academic from Boston actually managed to cross-link some publicly information data with some so-called anonymized health records of a public hospital to reverse engineer and get the data, everything about the health records of the governors of Massachusetts. So this is basically just saying that some of very old techniques that people thought it is safe to do is not safe at all. This slide is also taken from US Census Bureau. It is not only that some people or some organizations that maybe were not familiar with the way, how to anonymize data did some things that didn't work, even at the level of government agencies that were responsible for protecting the privacy of individuals. Before 2020, they simply aggregated data, the census data, and created some aggregate tables, and then they released those tables as if it is safe. But we now know that actually, if we have aggregated a few properties of, let's say 10 or 20 individuals, or even more individuals, if there is even bigger tables, these correspond to some linear equations, or, some equations. It could be nonlinear even, but you can actually reverse engineer that with the computational powers that exist these days to be able to decouple all these aggregate data and get the information of individuals. So again, just to say that existing techniques didn't work. So differential privacy is one solution to address this situation and try to enhance the privacy of individuals in data sets. So what happened, I just don't want to provide a very high-level view of what differential privacy is doing. The main premise of differential privacy, as it was proposed about 2006, is that there is a central data curator, for example, having a large data set, think about US Census Bureau or some other government agencies that have a lot of, let's say, data about people. There are some adversarial or untrusted data analysts, and they ask questions from this data set. What is the average income of people in such and such suburb? What is the, average age or median age of people in this neighborhood, and things of this sort. So the query comes into the data set, and this curator has to answer. So differential privacy is a way to try to protect the presence or absence of people in this large data set by adding noise to the query. So there is a statistical perturbation that is kind of try to create plausible deniability in terms of whether somebody is or is not in the data set. So that is a very broad premise of differential privacy. Instead of providing the truthful response, you perturb the response and then release the response. So in very broad terms, this is what differential privacy does. In this talk, we are going to consider a special variation of differential privacy where actually the model of differential privacy is flipped. So what do I mean by flipped? We are going to look at it in the next slide. So the next slide is a distributed system, where instead of having a trusted data curator such as a government agency, we have an untrusted, a company, or maybe we don't completely trust, let's say, a company or a data utility provider, for example, Facebook, Google, Twitter, or things of that sort, that they are interested in users' data. So the data resides with the users. They are distributed in a network, and each of them is, interacting with the system. They have some, they are typing something on the browser. They are, typing a message. They want to share their data, with this untrusted central the company, for example, in return for, let's say, some recommendations about, browsing or where to browse, what sites are most relevant to their search, or autocorrection, or any other kind of data analytics that is relevant to them. So this is called local differential privacy, in the sense that the data is localized at these users, and then there is a central system that wants to probably guess some statistics about this data, and then return some utility to the users. So examples of local differential privacy is actually a Google report, which is using the ideas from local differential privacy. So what do we do? In the kind of idea, if the idea of differential privacy is to perturb or the data before you share it with somebody else, so it becomes natural to think that in a local differential privacy setting, if the true data of users is represented by X1, X2, or XK, let's say, before they share it with the data with the company, with the central untrusted company, they perturb their data. So they change X to Y, X1 to Y1, X2 to Y2, XK to YK, and then they share the perturbed version of this data with the untrusted company. So how can we model this? So we are going to get a little bit into the, modeling and mathematical framework of differential privacy. But before we do that, I just want to have one note that how maybe a little bit about the history and origin of local differential privacy, which actually goes way back to, before any of this was in the 2000s, it was relevant. So the history of local differential privacy in a kind of not in these terms or not in this such formal framework, but it can be traced back to 1960s, where psychologists wanted to design surveys and encourage participation in these surveys if the survey involved some sensitive query. For example, let's say use of illicit drugs or something that people were uncomfortable answering truthfully. So instead of getting truthful answer all the time, they kind of encourage people that they could actually lie. And then they participate in the surveys much more broadly. So the participants were asked to respond truthfully if their answer was non-sensitive, if they had nothing to hide. Basically, they would respond truthfully. That's one way that you could implement this. This is not the only way, but it's one way. However, if their answer was sensitive, for example, they had done something that they were like not exactly legal, then they would toss a coin, a biased coin, let's say 75%, let's say head and 25% tail. If it was head, then they would respond truthfully. And if it was tail, then they lied. They flipped their answer and then they said, no, they didn't use anything. So this is one way that, a kind of the origin of local differential privacy usually is in the literature is traced back to this work. So how can we formalize it, more generalize it, and say what we can do? So you can see that there is this kind of perturbation. Is very, for people who are familiar with communication systems, you can actually see that you can represent this by a communication channel. So there is a channel, a transition probability matrix, or a mechanism, so to speak, in privacy language, where C sub X and Y is the probability that you actually denote, you output something Y, given that the truthful response was X. So these are the probabilities that you perturb your data according to this channel transition probability matrix. So all good in terms of as far as people are concerned in terms of mathematical framework. This is all should be familiar for people at least with communication background. So let's see two examples of these channels. Let's say that the secret is whether you liked or didn't like a particular product. And the possible answers is yes, you liked it, maybe, or no. So you could perturb these. Let's see two possible examples of these channels. Channel 1 is shown on the left, and if the true response is Y here, then you might respond yes, or maybe, or no with those raw probabilities, which sum up to 1. And on channel 2, you have another type of probability that you might respond with those. And both of them are valid channel matrices. So it's all good. The question that we are kind of trying to lead up to the work that we have done is asking, we are talking about differential privacy. So one might ask, how do we even measure or define local differential privacy? So the question is, if I ask you which channel is more locally differentially private, you first ask me, okay, what is the definition? What do you mean by that? So we haven't answered this yet, but we are going to get into that. So this is kind of the first starting point to say which one of these channels is more private, right? So, and in particular, more locally differentially private. So let's talk a little bit about what the literature says. So in the literature, there is a single value that is associated with each of these two channels. And this value is usually represented by a parameter that is called epsilon. So a central claim in both central and local differential privacy is that the lower the epsilon, the better the privacy, right? So if I have channel 1, which has epsilon 1 associated with it, and if I have channel 2, which has value epsilon 2 associated with it, is if epsilon 2 is less than epsilon 1, you say the central claim of differential privacy is that C2 is more private, more locally differentially private. But what we are asking is it really always more private than channel 1? Is channel 2 always more private? So this is kind of our motivation to try to get into the details of this epsilon. So I want to tell you a real life example, and hopefully that will more motivate what I'm talking about. I hope that this will become more, kind of understandable. Is that, let's say you have gone shopping and you come up, you go pass by two stores. One of them has a sticker on their window, nothing over $100, and the other store says nothing over $29, right? And then the question is, if you go to store two, are you guaranteed to buy something that is cheaper compared to if you went to store one? And I hope that you understand that this is not necessarily true, and you might get trapped into something, get something that is more expensive, the same item even, that it could be 25 here and 23 over there. So it's really no guarantee that you could end up being better off if you went to store two. So I hope this is kind of clear. So what does it mean then? For example, we could say that if we know exactly what we want and we have the time to go and explore both the stores, let's say, we could end up getting a better deal in store one even, right, compared to store two. So that sticker should not be the only factor that we decide, in terms of what we buy. However, if somebody puts a gun to our head and say, go and randomly choose an item from one of these stores, and you only have $29 in your bank account, then you know that you should go to a store. So it depends a little bit on the setting and what you want to achieve and what your goal is. So there is a lot of nuances that one needs to take care of and take into account when making some decisions about the privacy and maybe shopping. So I hope this kind of sets the setting, what we may want to do. Now let's go back to the privacy situation. I said this epsilon parameter is the single value. How is it calculated? Is the ratio between the values of the channel transition probability matrix that at any given y, you compute, this ratio between any x and x dash, any two secret values. And then if for every pair of x dash and for every y, it is lower bounded by e to the epsilon, then you say that this channel is epsilon locally differentially private. Okay, so that is definition, or so it's an upper bound. So the takeaway message that I kind of want you to have with you is that this e to the epsilon is a little bit like the upper bound, or this upper bound is a little bit like the sticker that you may find on store shops. So that is kind of the very broad message that I want to get across. And our contribution in this work is to kind of try to, we are providing an explicit characterization of the most pessimistic max case Bayesian attack that can actually happen in such a channel and related to that sticker value. So it is analogous to finding the most expensive item in each of these stores. Let's say, what is the item that achieves that particular the highest price. So let's go back to our examples. So if you were to calculate the ratio of the channel transition probability matrix for each possible value of the output, you would see that you would get 4, 2, and 4 in the, sorry, some of the lines are exactly on the, I hope you can see for people who are here on the line, but 4, 2, 4, so the maximum is 4 for channel 1, and for channel 3, the maximum ratio between the maximum and minimum in each column is 3. So therefore, channel 2 has a value of e to the epsilon equal to 3 versus channel 1, which has a value of 4. And the question is it kind of in the same direction? Is channel C2 always better than channel C1 because it has lower epsilon? And I hope that by now you could at least agree with me on a very kind of intuitive level, and based on the arguments that I provided, that it is not necessarily. And that's what we want to kind of delve into and try to categorize different attacks that may happen that go against these relations, right? So that is what we are going to do in the next in the remainder of this talk. So okay, so let's see what happens. So this is the remainder of this talk is going to be two things. First, we are going to construct Bayesian attacks where channel C1 performs better, which means provably leaks less information than channel C2 despite having a larger epsilon value. So that is our first goal. And the second goal is to establish an operational worst case, max case leakage, meaning it's a capacity results, the privacy capacity result, meaning for the epsilon measure in local differential privacy. So first we are going to show what are the inconsistencies and then try to say, okay, despite these inconsistencies, epsilon value has a clear operational Bayesian attack attached to it. So with these two goals, let's move on. So for people who may not be, maybe the concepts may not be fresh, let's say, in their minds, I just want to summarize what I mean by a Bayesian attacker. So there is an adversary who has a few following properties or actions that is associated with this. With it. So first of all, it chooses a prior belief pi about how the secret is distributed. So that is one key ingredient of a Bayesian attack. The second one is that the attacker is interested in maximizing a gain function G, either on average or in the maximum sense. And I will provide some examples of this. It knows the channel C, the channel transition probability matrix is actually publicly available. Once you want to perturb your data, you agree on what channel it is being used. So channel C is known between the parties. And then, therefore, the adversary can, once you observe a particular Y, a particular output, then you can adjust your belief about the secret as the posterior, which we denote by delta sub Y, about the secret. So you observe a particular Y, and then you adjust your posterior belief. And then the leakage can be computed in different ways. One way of computing it would be the ratio of the posterior gain to prior gain based either on average sense or maximum sense. So these are the ways that kind of make up a Bayesian attack. So let's see an example. Here, there is an adversary who chooses a particular gain identity function where wants to guess secret X as W and is only, interested in correctly guessing the secret. So the gain is all the eggs are input in one basket, basically. So you say the gain is 1 if you correctly estimate the secret, and 0 if you don't correctly guess the secret. So that is the gain function. And let's say that the adversary assumes that, in our example of yes, maybe, and no example, assumes that this prior distribution is equally likely. This could come from maybe some prior public knowledge that on average people like this product 1/3 of the time, maybe they like this product. So there is some kind of publicly available marketing data on what is the distribution of people liking a particular product. So pi, let's say, is 1/3, 1/3, 1/3. So if the gain is like that, the only guess is the, correctly guessing. But because the distribution is equally likely, there is no, any guess is as good as any other guess. So before observation of Y, if you don't have anything else other than the prior distribution, any guess is as good as any other guess. So you might as well toss a, a three-way coin and decide which one of them is the actual secret. However, if you were to observe a particular Y, then you can adjust your posterior according to Bayes probability rule, to find out what is the probability that secret is X given that your observation is Y. And then you could then take another maximum likelihood estimator. So after observation of Y, your best guess is the maximum secret that, maximizes the probability of the posterior for that particular observation Y. So I hope this is clear what the actions of the adversary is for this particular gain function. So if you were to see some examples, this is for channel 1. So for channel 1, I have computed without the details, I have computed the posterior, and these are the values, the probabilities of each of what yes or maybe or no can occur based on equally likely input secrets, and that is the same thing is done for channel 2. So these are kind of what you could do for a Bayesian attacker would do, and the ones that I have shown are in red are the maximum you see in this distribution. 4/7 is the most likely outcome. 1/2 is the most likely outcome. So the attacker would revise its posterior belief and guess the distribution like that, the most likely secret like that. So I hope this is clear. So then there is a result that is not by us, it goes back to more than 10 years ago, which talks about the maximum leakage in average sense. So the key word here is average. The highest average leakage from a channel C to a Bayesian adversary is achieved by an adversary with the identity gain, the same gain function that we showed as an example, and with uniform prior, actually. So though the adversary that I showed you is the worst case attacker in the average sense, and the amount of leakage to that attacker is characterized by the maximum value of the channel in each column, and then you sum it up across different columns of the output. And this notation, you can ignore it. It's just a notation to show this maximum leakage, but it is called base capacity. So it's a capacity value in the sense that any Bayesian attacker, no matter what they do, they cannot get more information than this bound in the average sense, okay? So let's look at those two examples, our favorite toy examples that we have, and compute the base capacity for them. So the base capacity for channel 1 is the maximum in this column, which is 2/3, plus the maximum in this column, which is 1/3, plus maximum in this column, which is 2/3. So it amounts to 5/3. And for channel 2, it is symmetric. So it is 3/5 times 3 is 9/5. So you compare them and you see very quickly that actually channel 1, the highest leakage in the average sense is smaller than the highest leakage in the average sense from channel 2. So because 5/3 is less than 9/5. So this is despite the fact that channel 1 was having a larger value of local differential privacy. So they completely go against each other. They don't correspond to each other. They are not consistent with each other. And it is any Bayesian adversary in the average sense. I didn't particularly choose a particular adversary, any class of adversary Bayesian in the average sense. So if I were to compare it to my store analogy, it's kind of like saying that there is a class of products, let's say all jeans, in one store that are store 1 that are under $20, whereas there exists a gene, some jeans in store 2 that are strictly more expensive than $20. So I have identified the class of products and compared them in these two stores, and I could say with certainty that if you're interested in this class of products, you should maybe you should better you go to store 1. Right? But again, this is not completely deterministic. It is not completely saying that you should definitely go to store 1. There is some nuances here as well, because if you are interested in a particular gene, particular color and size and brand, you might still need to go and check them out, in between these two stores. So there is even nuances in this statement that I make, but at least I have been able to find some inconsistencies between the value of epsilon and what Bayesian attackers may do, right? So that is this class of attackers, but some proponents, some people that are very well embedded in differential privacy may ask me, you only talked about average Bayesian attackers. What about worst case Bayesian attackers? What about if I don't care about the leakage in the average sense, but I'm interested in leakage in worst case sense? What happens there? Because it is kind of roughly understood in the literature in differential privacy that differential privacy is a worst case leakage situation. So let's consider the same toy example, but this time don't worry about the probability of those Y's, those observations occurring. Regardless of how likely this yes or maybe or no outcome might be observed, I don't care about those likelihoods. I only care about the amount of leakage to a particular adversary who may guess these values, right? So I don't worry about the likelihood of a leakage. I only worry about the value of the leakage. And then I want to see how these two channels compare. So from the first channel, I only worry about the maximum across all possible Y outputs of that posterior probability. So the maximum is the maximum of this 4/7, 1/2, and 4/7. So the maximum is 4/7. And this is a symmetric channel, so the maximum of these three is just 3/5. So again, you see that 4/7 is smaller than 3/5. And even in a maximum sense, there exists an adversary that for which channel 1 leaks less to that particular adversary compared to channel 2, despite having a larger epsilon value. And this is in maximum sense, okay? So again, if we were to kind of look at the analogy for the store situation, what we have shown is that there exists, let's say, a particular T-shirt in store 1, which is priced at $23, and the exact T-shirt, same brand, same size, everything identical, is priced higher in a store 2. So we have also been able to characterize such an attack, let's say, in store 1. So depends on what the goal of the adversary is here. So the analogy has some limitations, but I just try to kind of make it a little bit more amenable for people to understand. So how am I going with time? We have maybe 5 to 10 more minutes. Sorry?
Up to 25.
Up to, okay, right. So let me see. As I don't have actually, the rest becomes a little bit technical, but don't worry about the details. If you don't, the purpose is not to understand this formula, but the purpose is that to say that there exists a formal definition of max case leakage, where very broadly speaking, the denominator is the prior leakage and the numerator is the posterior leakage in the maximum sense. So there is a gain function, there is a posterior probability. This is the action of the adversary trying to maximize what is the best guess. And this is a maximum over all possible values of Y. So this is kind of the breaking up the components, but it doesn't matter. We don't need to understand this, but just saying that there exists a maximum leakage definition. One of our first results is as follows, trying to link this to a very important notion, both in learning and in information theory, which some people know as lift, and I have defined it here. Lift is nothing but the maximum value of the ratio of the posterior probability of X after observation of Y, to the prior probability. The maximization is over all values of X and Y. This, of course, as you can see, is a function of the prior. So the prior distribution is a function, is an argument here, and of course depends on the channel, because for computing the posterior, you need to know the channel. So this value of the lift, if you ignore this maximization, actually the average of this lift is nothing but the mutual information, like Shannon mutual information. If you averaged it over the joint distribution of x and y, the log of it, of course, it would become Shannon mutual information. But here we are interested in the highest value of this ratio, right? So, so lift, how is it related to this thing, this quantity, is one of the key things that kind of comes to play. So one of the first results that we are showing is that there exists an explicit G function, gain function by an adversary, for which for any channel C and any prior pi, the max case G leakage is equal to the lift. So what we are saying is that there exists an adversary out there that for any channel transition probability matrix, it can, and any gain function that any prior distribution that it can choose, if it matches the gain function to its particular prior that it chose, it can achieve the worst case, this max case leakage, right? So this lift is an achievable leakage. That is all we are saying. The value of the lift can be achieved by adversaries, right? So that is one key thing. The other key thing is that how about, the general relation? This is an equality relation, but what about the general relation? The general relation is also as follows, that the lift provides an upper bound on max case leakage. So means that there is no maximum case leakage that can ever go beyond the value of this maximum ratio of posterior to prior. And it is also achievable. So lift is a very strong quantity, a very strong upper bound on the value of leakage from any channel, okay? Then the last piece of the puzzle that allows us to combine everything and to provide an operational meaning for epsilon differential privacy is as follows. It is something called lift capacity. Remember that I said lift is a function of both prior and the channel. So if you try to take out the dependence on the prior, you come up with a quantity that is only a function of the channel, where you take out the worst case prior. What is the worst case prior that results in the highest lift? You call it lift capacity, okay? Which is kind of trying to abstract away the actions of the adversary or the assumptions of the adversary. It says no matter what the adversary does, the lift cannot go, or what assumes the lift cannot go above the value of lift capacity. Then this lift capacity is what becomes equal to the value of epsilon in local differential privacy. So putting everything together, the main result of our work is as follows. To say that I give you a channel C with the value of epsilon, there is an equivalence between the upper bound that you can get from local differential privacy and the upper bound that you can get on the value of the lift capacity. So this tells you that that sticker, that value of upper bound, is the highest lift that you can get across all possible prior distributions. And that possible lift is achievable by a very bad adversary that chooses that particular lift and chooses a particular gain function, and therefore can achieve a very high max case leakage attack. Okay, so these two are equivalent, and this side has an operational meaning in the sense of achievability by an attacker with a particular prior and a particular gain function, right? So that is kind of the whole thing coming together. And as a takeaway message, all I want, perhaps for this talk to get across is that the value of e to the epsilon is equal to the highest. It has a capacity quantity associated with it. Is the highest max case Bayesian leakage from the channel. You cannot go above this value in terms of Bayesian attacks, but there is only one particular attacker that can achieve this. Not everybody can achieve this. But there is kind of, if I want to show you the store analogy, is that basically, unless the store one owner is very bad at marketing, it is safe to assume that there exists an item in store one that is costing $100, right? I mean, it would be silly for the store one to put a sticker that is nothing over $100, and every item in their shop was below, $75. It would be a terrible marketing, right? So this is kind of saying that this is about existence and construction of that. What is the highest? What is the most expensive item in the store? And if what I would even go further is that it is probably a good strategy to try to have a lot of items between $29 and $100, because otherwise, if there is only a single item that is valued at $100 and everything is below $29 in store one, you might as well pull that item, try to adjust your channel, try to pull that item from the shelves, and then try to have a similar kind of advertisement as the other store. So there is a lot of nuances about understanding what type of attacks you are interested in protecting against, and try to perturb or massage the channel distribution such that you kind of can show a competitive epsilon value in the market. So this is somehow a bit of design is needed. So you need to kind of be aware of who you are comparing against. So with this, I'd like to basically conclude, because I think there was lots of, there is one extra slide if you are interested. I can talk offline, but there is still a remaining challenge about understanding this value of epsilon. Epsilon is still, we try to make it an operational, give it an operational meaning, but rarely do we know how to choose a particular value of epsilon, how to choose the channels, how to, in the end, I showed some bounds, but it is really not very clear how to design good channels that can protect against a wide range of adversaries. What we also did was, for local differential privacy, we don't know much about the central version of differential privacy and what kind of Bayesian attacks, it is protecting. But of course, there is some work, by both by my collaborators and by Sarah and Tobias that might be related to this, and I'm happy to kind of learn more about those while I'm visiting. And then more broadly speaking, I think maybe the ideas that we have presented here could be used for understanding other privacy measures in the literature from the perspective of information theory. So with this, I would like to conclude the talk, and thank you for your attention. I hope it was accessible. Thank you.